Hi guys, good morning. Only three of you are there. Shall we wait for 2 more minutes? Let people join.
Yes, sir.
Yeah. So in maths and physics, how's it going, people? Like how many chapters have they completed in physics? Any idea?
Physics around 5, sir.
5 chapters. Okay, math.
Math 4 to 5, sir.
Okay. Now what chapter is going on in physics?
I was absent for the last class, sir. I don't know.
Okay. Anybody else knows what is happening in physics? Which chapter? Srivatsan, do you know?
Sir, I was only absent, sir.
Oh, you're only absent. So Siddharth, do you know? I think Siddharth, some problem.
Rotational mechanics only.
Okay, rotation mechanics. Okay, fine. Yes, if you have your friends' number, please text them and ask them to join soon. Okay, so we'll start right away. Let them join whenever they want to join. I think Harini joined now. Good. Harini, if you have people, other girls' number, can you please call them and ask them to join? Yeah, Hari is joined. Yeah, now people are joining. Okay, cool people. We'll start right away. I'll share my screen. Okay. One second, guys. Right. So we have been saying thermodynamics, right? So I think yesterday was the day we just started it, right? Uh, yeah. So okay. So I want everyone, like not everyone, like I want everyone to tell me what we saw last class, whatever you remember. Just quick, tell me your points. Each one of you one point. Quick, go for it. Yes, what we started with thermodynamics.
Types of system.
Okay. Types of system. Okay. Types of system. What are the three types? What are the four types of system?
Open, closed,
Hmm.
isolated, and
Hmm.
adiabatic.
Yes, absolutely. Right. So then, okay, those are the four types of system. And then we said boundary, surroundings, all those things we spoke. Okay. After that.
intensive and extensive properties of a system.
Correct. So we went on to see the description of a system. In that we saw properties. So there are two types: intensive and extensive, right? So intensive properties are going to depend, are independent of the amount, and extensive properties are going to be dependent on the amount. Okay. Now there is one more way of classification of properties or variables. What is that?
State variables and path variables.
Absolutely right. So we have something called as state variables and path variables. State variables just depends on initial state and the final state. Again, when I say state, it is talking about the conditions: pressure, volume, and temperature, right? And path variables depends on the initial state and final state, and also how you reach there, how you reach from state one to state two. Those things also matters, right? And examples can be, for example, for your what is that state variables, say all your enthalpies, your entropies, all energy, basically all energy variables will be under state variables, and path variables like heat, work, all these will be path variables, right? Okay, then we went on to see, okay, what is the next thing we saw?
A zeroth law of thermodynamics.
Right. So we saw zeroth law of thermodynamics. So it's all about thermal equilibrium. It's also called as common sense law, right? So we had three bodies and all those things we did, right? Okay. Then we went on to see, I guess, the relationship between Q and temperature, that is heat and temperature, right? So I think we ended up with this equation. So Q, what happened? 1 second. So Q, we got this equation, N CV del T plus N CP del T, right? So this is the last equation which I told you, but anyways, like we can get it from here. So we know that Q is an extensive property. That means it is going to depend upon the amount. So we include the number of moles also, but I told you in physics, we'll not be using this much. In physics, we'll be going for mass. So the name of the heat capacity also will change, right? So there it is going to be called as mass heat capacity. Now here it is going to be called as molar heat capacity, right? So we have it, the heat capacities are basically going to be, we even gave a definition for heat capacities, isn't it? So it is the amount of heat, amount of Q required to raise the temperature of the substance, 1 mole of the substance, by 1 Kelvin, right? When the change in temperature is 1 Kelvin, and when the number of moles is 1, Q becomes equal to C, right? Okay, so now the CP and CV are going to come into the picture depending on at what conditions I measure the heat capacities. If I'm going to do the process at constant volume, then it is going to be CV, heat capacity at constant volume, and CP is going to be at constant pressure, right? Okay, then we went on to see, I guess, the first law of thermodynamics. Oh, no. In CV itself, we saw so many things, right? So I told you the heat conductivity or heat sensitivity of a substance is going to be inversely related to the value of the heat capacities, right? Okay. And I also said that the heat capacities are going to be directly proportional to the atomicity of a gas, right? So basically a monoatomic gas will have lesser heat capacity, diatomic gas will have a little higher, and a polyatomic gas is going to be little more higher, right? Okay. And I also said you that this heat capacities are going to be directly related to your amount of motions that I can have in the gaseous atoms, right? So there can be three types of motion: translational, rotational, vibrational motion, right? So each of these motion is going to contribute some value to the CV, right? So I told you, if you can remember, the for translational motion, it is going to be 1.5 R, and for rotational motion it is going to be 0.5 R, and for vibrational motion it is R, right? So when it is a monoatomic gas, I can have only translational motion, right? If it is a monoatomic gas, only translational motion. If it is diatomic gas, both of them, that is translational, rotational. And for a polyatomic gas, all the three will be there, and accordingly I'll be getting 3R as the heat capacity CV value for the gas, polyatomic gas, right? Okay, these values you have to remember, people. Nobody will tell you in the exams, right? All these values you have to remember. Okay, Fine. So that's about heat capacities. I think then we went on to see the first law of thermodynamics. It's just the law of conservation of energy. Law can mean energy can neither be created nor be destroyed, but it transformed from one form to another form. We saw the mathematical equation, mathematical form of first law. So that we said it as delta E is equal to Q plus W, right? So delta E, we know what, like we even went for what is this delta E? Delta E is internal energy, change in internal energy. So we know this E, internal energy, absolute internal energy is nothing but the sum of all the potential energies plus the sum of all the kinetic energy present in the atom, right? So basically Ke translational, Ke rotational, Ke vibrational, along with your potential energies, you'll be able to, able to calculate. That's how we define your internal energy. And I told you, how will you interpret this particular statement is the change in internal energy can be brought out, right? If you have, say, some heat supplied or heat lost, or when the system is doing some work, or when someone does work on the system, right? Okay, so this is the thing. And then we went on to see what is this W, right? So we said W, we had a formula for that. It's minus P external del V, right? Minus P external del V. And you have to be very, very careful. This P, well, the pressure value which you're going to substitute here is not the pressure of the gas, it is the external pressure, right? And then we went on to see what are the sign conventions, right? So sign conventions we saw for Q and W, right? So we told heat gained or heat added is positive and heat lost is negative, and work done on the system is positive, work done by the system is negative. Or in other words, whenever expansion happens, the work is negative, or whenever compression happens, the work is negative. Sorry, work is positive. Okay, right? Now, people, you will have slight modifications of this sign convention in physics, right? For Q, it's okay. For Q in chemistry and physics is going to be exactly same. But if you go for W, there it is going to be opposite. Work done by the system is positive and work done on the system is negative. Then the sign convention is different there. But anyways, you will not be using much of thermodynamics in physics, like as much as what you use in chemistry. But anyways, right, you have to remember that. Okay, so I think this is where we stopped last class, right? Okay, now we'll continue. We'll take on from here, right? Fine. So now what we do is, now that we know the first law, right? Now that we know the equation for first law, right? I'll be able to derive, or I'll be able to modify this first law equation for different kinds of processes. Okay, say I can have something called as isobaric process, that is constant pressure process, isochoric process, constant volume process, isothermal process. All these things are there. But before we move on to see that, right, there is one important thing which I want you to know. That is this process which I'm talking about, any kind of process for that matter, right, or any kind of work which is done, right? All these can be categorized into two types. One is what is called as reversible processes, right? Reversible. And I have something called as irreversible processes. Okay, now from the name I think you'll be able to understand it's like reversible and irreversible, but not exactly how it works, right? Now let me tell you in this way. So whenever I talk about irreversible process, people, right, all irreversible processes are very fast processes, right? Very quick processes. Okay, like what? Okay, now now in case of reversible processes, they are very slow processes. Okay, right? And they are very slow processes. Okay, and since it's happening very slow, right, I would say at each and every point, at each after, say, it is going to be, I would say, a combination of infinite number of steps. Okay, a reversible process is going to be a combination of infinite number of steps. And after each of these steps, since the process is happening very slowly, I would say a reversible process at all the points is not very far away from equilibrium. Again, I repeat, right? So a reversible process is a combination of so many processes, so many millions and billions of steps, right? And all these steps are pretty slow, right? And because of that reason, say you went from step 3 to step 4, you went, right? And this happens very slowly, right? That you will be able to easily come back to step 3. That means at every point, at every step of the process is almost going to be at equilibrium, at least very, very close to equilibrium, right? Okay, now if at all you want to understand a bit more, let me illustrate you with an example. Okay, right. So let me look at this, right? Say I have gas in a piston arrangement, right? And say I have a stopper here, right? The piston cannot move above that particular stopper. Uh, Now what I do is, okay, so now assume that this is in equilibrium with a 10 kg mass. Okay, right? This is the setup, right? So the piston is here. Now obviously now when I say equilibrium, the pressure supplied from by the gas is going to be same, but the pressure is going to be same from the top also, right? The 10 kg mass pressure and the pressure applied by the gas is going to be same, and that's why your piston is in the stable position, equilibrium position. Okay, now I also assume that the initial state or initial condition is P1, V1, and T1. Okay, P1, V1, and T1. These are now this P1, V1, T1 are the pressures and volumes and the temperature of the gas. Okay, right. So now what I do is I remove the 10 kg mass. Right? I remove the 10 kg mass. Now I know what will happen. What will happen if I remove 10 kg mass?
Piston will move up.
Yeah, right. Obviously now the piston will move up, right? So obviously the piston cannot move to anywhere where it wants. So now after I remove it, the piston would be here, right? Now the stopper would have stopped it, right? And the piston is here, right? Say now the final condition is say P2, V2, and T2. I don't know, like it depends. It depends on the process whether I have isothermal or something like that. But we just assume that the conditions changed. Okay, now this is an example for a perfectly irreversible process. The moment you remove the 10 kg mass, right? The moment you remove the 10 kg mass, now it is going to hit FUT. It is going to hit the stopper and it's going to stop very fast, very, very spontaneous, right? Okay, now same thing. I will try to do it a little bit slowly. Okay, now how can I do that? Let me do it this way. Again, I have the same piston arrangement, same gas, same amount of gas. And now what again I have the stopper, right? Now what I do is instead of putting a 10 kg mass as a whole and making it equilibrium, I am going to put two 5 kg masses, right? I'm going to put two 5 kg masses on top of this. Okay, now again the same initial condition, pressure P1, V1, T1. Initially here also it's the same, right? Now what I do is that I remove the first 5 kg mass, right? Then what will happen? The piston will slightly move up, right? Now if I remove the second 5 kg mass, right? The piston will again go to P2, V2, and T2. Again, the piston will go over here. Again, it's P2, V2, and T2. Right? So now you can understand I have done the process a little bit slowly. Instead of using 110 kg mass, I increase the number of steps. I did it in 2 steps. First 1 kg, sorry, first 5 kg, second 5 kg. I can make the process a little more slowly also if you want. Say now I have, say 10 1 kg masses, right? So this is 10 1 kg masses. Again, I'll have the stopper, same thing. Again, initial condition same, P1, V1, and T1. Here also it's same, right? So now again, what I do, first 1 kg mass, very slightly moving up, second 1 kg slightly. Now the 10th 1 kg mass, if I remove, again, the piston is going to move here. Hey, what happened? Okay, the piston is going to move here. Again, the final condition is same, P2, V2, and T2, whatever you saw in the first case, right? So now what happened? Now you did the process with still more slowly, 10 steps you included, right? Okay, now I can make it still more slower if you want. I can make 100 times of 0.1 kgs. First 0.1, second 0.1, 50th 0.1, 100th 0.1. Again, it's going to reach P2, V2, and T2, right? So what you observe here, people, what you're observing here is that I have same initial condition, same final condition, but how you do the process is actually different. right? So the first case, when I had only one 10 kg mass, it's an absolutely perfectly irreversible process, right? So as I go and make the process slower and slower and slower by increasing the number of steps, right, it is actually reaching the reversible conditions. I am doing the process as slowly as possible, right? So if I have 0.01 kgs of 1,000 times, right? So hope you understand how slowly the process will happen, right? And obviously now if I have this, even if you look at this 1 kg, now after I remove the seventh 1 kg, right, and again I put it back, so you will not see much of difference, right? That's why I say that at every step, at every point of the process, the system is not far away from equilibrium, right? Okay, so this is the difference between a reversible process and a irreversible process. Okay, now same thing. Now the question is, people, what happens, right? What happens, like if I see it in form of a graph, right? What will you observe, right? What will you observe if I put a PV graph, P versus V graph, right? For a irreversible process, for a reversible process, right? What is going to happen, right? How will you visualize? What are the differences you will see, right? Now, before we move on to see that, right? Now, in a question, if it's a problem given to you, right, now how will you understand whether the process is going to be a reversible process or an irreversible process, right? That's the question which comes to our mind, right? Now it's pretty simple, people. Now please look for this phrase: under constant external pressure, right? So this phrase you have to look for, right? Under constant external pressure, right? Whenever you see this term, this indicates that it's an irreversible process, right? Now why do we say like this? Now it's pretty simple, right? Now as soon as you remove the 10 kg mass, right, and when you remove the 10 kg mass, there is only one pressure, only one next what is it, only one external pressure which is happening, only one external pressure which is getting uh, supplied here, and that would be my atmospheric pressure, right? So please understand that. So like under constant external pressure means as soon as you remove the 10 kg mass, right, so the piston expands, the gas expands under one constant external pressure, and that is my atmospheric pressure, right? But when you go for this case, when you go for the next case, right, or when you go for the 1 kg, or when you go for the 0.1 kg case, it is not exactly true, is it not? Say when you remove the first 5 kg mass, right, when you remove the first 5 kg mass, obviously the pressure will be due to the in this the next 5 kg mass, right, as well as the atmospheric pressure, right? So obviously there you don't have constant external pressure, right? Same goes here. After removal of first 1 kg, there will be some other different pressure. After removal of fifth 1 kg mass, again some other pressure will be the external pressure, right? So whenever you see this phrase under constant external pressure, that actually tells you that it is going to be an irreversible process, right? And if they don't specify anything also, right, if they don't specify anything, again by default it's going to be an irreversible process, okay? But if it is going to be a reversible process, they will specify in the question it's a reversible process, they will specify by words, so you don't have to worry much about it, okay? Right, so let me go to the graph and see how it looks, how the graph looks, right? Say now I'm gonna have a PV curve, pressure, volume, right? So let me draw it for a irreversible process, right? Okay, now what you see is an expansion, right? So obviously the initial volume will be somewhere here, and say the final volume is somewhere here, okay? Right, initial volume and final volume, because it is undergoing expansion, right? Now this pressure what you are putting is the external pressure. Please be very careful. Right, this is my external pressure. Be very careful, right? So initial, like say now we're going to start the graph. As soon as I remove the 10 kg mass, what happens is what we are going to see, right? So as soon as I remove the 10 kg mass, say assume that the external pressure is somewhere here, right? So as soon as I remove the 10 kg mass, this particular point where I have marked in the y-axis, that is my pressure, external pressure, Okay. Now this pressure, this external pressure, the point which I have marked is not going to change, right? It is not going to change, but the volume of the gas is going to change, isn't it? Because it's undergoing expansion. Correct, right? Am I doing it correctly? Oh, wait, let me actually, this should not be this big of a pressure. This should be, let me once again. Okay, right? So this is actually going to be a small pressure, isn't it? Because there's just atmospheric pressure. Let me mark it here. That would be better, right? Fine. So now what happens? Now do you see that now the gas is going to undergo expansion and this value is not going to change. So can I say the graph looks like this? Yes or no? Any doubts how the graph is like this? I obviously have to put an arrow mark. That's very, very important in thermodynamic graphs, right? You have to tell that it is undergoing expansion. Volume is getting increased. Yes or no? Everybody understood why the graph is like this?
Yes, sir.
Right? So because it is going to be constant external pressure and that value is not going to change throughout the process, in the sense, even though it's going to be very fast, right? So it's going to be under constant external pressure. Okay, right, fine. Now the same graph in the same diagram, if I try to extrapolate, if I try to plot my reversible process graph, right? So then we'll see how it looks, right? Say now let me take the 10 1 kg masses. Okay, right? So 10 1 kg masses. Say now we are going to start doing the graph right after the removal of first 1 kg mass. Okay, right after the removal of first 1 kg mass, I am going to start. So definitely after removing the 10 kg mass at once, definitely the pressure is less, right? But if I have removed only 1 kg, definitely the pressure will be more. The external pressure is still more. So they say it starts somewhere here, right? This is the point where it starts for the irreversible process. The first 1 kg mass removed, and this is the external pressure. And the volume is still same. Initial volume same, final volume same. That is not going to change, right? So now what is going to happen? Now what will you see is that obviously this is the last pressure also, right? The final pressure, the final external pressure is still the same, right? After removal of the last 1 kg mass, again the external pressure would have been just equal to the atmospheric pressure. Okay, right? So fine. So after removal of first 1 kg mass, this is the pressure. Now I've obviously after removal of second 1 kg mass, I'll have some other pressure, third 1 kg mass, some other pressure. So many intermediate pressures are going to come in between these two, right? And the volumes are also going to be included. So if you look at the graph, people, right? The graph looks like this. Wait. Not exactly like this. It is going to start with the volume, right? This volume you have to start. So say somewhere here or somewhere here, it's going to start. And yeah, this is how the graph looks. Now, why do you see a difference in these two graphs? Is because again, I have to put the arrow mark, right? So why do you see differences in graph? Because after each and every step, the external pressure is changing for a reversible process, but for an irreversible process, it is going to be at constant external pressure, right? Okay, fine. Now, if I want to find the work done, W reversible and W irreversible, if I want to compare, obviously now when the gas is undergoing expansion, so definitely some work will be done in both these cases. Now the question is, people, now think and tell me which W reversible is greater or W irreversible is greater. W reversible is greater or W irreversible is greater?
Reversible.
Okay, fine. So if you don't know this, right, say whenever you have say work done in terms of your F dot S, if you do that, and basically if you plot a graph between F and S, right, now how will you find the graph? I mean, how will you find the work done? I hope you remember this. You just have to go for your area under the curve, right? Because dW, I can write it as F dot ds right? Same way, this W, dW, I can write it as P external integral dV. Say now, if I put an integral here. Okay, so we know whenever integral comes into the picture, we have to go for area under the curve, right? So this is exactly what we do. So if you can understand the area under the curve for an irreversible plot, say now if I mark these two, this would have been the area for the irreversible process, right? And say if I take some other color and do it, right? So this entire area would have been the area under the curve for the reversible process. Okay, so obviously from the graph you can see that the work done during an reversible expansion is greater than when you do a irreversible expansion, right? Okay, now what about compression? That's a good question, isn't it? Now, what about compression? Now, there will be a slight change in the graph. Now, it's like assuming that I'm going to do the exact reverse process, right? I add 110 kg mass at once, right? The gas is going to get compressed, or say the next step would be adding two 5 kg masses, first 1 kg, I mean, first 5 kg, second 5 kg, or say 10 1 kg masses consecutively getting added, right? So now the graph will look something like this. Let's P external, right? And this is volume, right? Now people understand, you will not see much of a difference in your reversible graph, but you are definitely going to see a difference in your irreversible curve, right? Fine. So you can also try and you can just tell me whether you got it right or not. Now please understand, now we are going to start obviously saying now it is going to be compression, say initially some volume, this is V1, and say finally some volume V2, it is going to go in compression, right? Okay, so please understand people, this external pressure which you're talking about for the irreversible process, that constant external pressure, that pressure is going to come into the picture right after you add the 10 kg mass, right? So obviously the pressure you saw here was pretty less because this pressure was after removing the 10 kg mass. Now this pressure is going to be pretty high because this pressure is due to the pressure of the 10 kg mass after adding it, right? So now how the graph will look, again this pressure is not going to change because it's an irreversible process. So you will see a graph something like this, and the arrow mark is very important. This is the arrow mark, right? Okay, now if I go for the reversible case, right? So now what will happen? Initially the pressure is very small for a irreversible. When I add the first 1 kg mass, second 1 kg mass, third 1 kg mass, fourth 1 kg, and after finally 10th 1 kg, the pressure is going to reach there, right? So now how the graph is going to look? The graph is going to look something like this, right? And obviously this is the arrow mark, right? Now if you look at which is going to have higher work done, I think from the graph you'll be able to understand. So this would have been, let me maybe make it black again, right? So this entire area would have been for the irreversible case, right? And for the reversible case, if I have to mark it, so reversible case will only be this area. I mean, you can understand, right? The entire area is included for irreversible, but only a small area is included for reversible, right? So in this case, in the previous case, we saw reversible work done was more, but in this case, reversible work done is lesser than the irreversible work done, right? So what is the basic difference? There it is expansion, and here it is compression. So whenever expansion happens, reversible work done will be greater, and whenever compression happens, irreversible work done will be greater. Is that cool? Right? So this
Sir,
is what you have to understand. Yeah.
I have a doubt, sir. I didn't
Yes,
understand
Tanvi.
how the pressure is constant in both the cases.
Okay. So the thing is, say now when I go for the expansion case, right? So please understand now when I remove when I talk about the irreversible case, when I remove the 10 kg mass, right? What is the external pressure acting there?
The atmospheric pressure.
Obviously it is not exactly open to the atmosphere, but whatever the pressure is in between, it is in the piston, that's what is going to act. And do you think as the piston is expanding at the time, I'm talking about the time in which the piston is expanding, in that case, do you think that external pressure will change?
No, sir.
Right, that's why we say it as a constant external pressure. But if I go for reversible case, right, what happened there? There are so many steps there. After removal of first 1 kg mass, there'll be some pressure. Second 1 kg mass, the pressure would have gotten reduced. Third 1 kg mass, still more reduced. That's why we don't say constant external pressure there. But in irreversible, there is constant external pressure. Yes,
Okay,
understood?
sir. So even if there's
Yeah.
a small change in the pressure in the system, we're not considering it because
No,
it's
yeah,
so.
exactly. Even if there's small change in the pressure, we are actually not going, we're not going to consider it, right? So there
Oh,
should be constant pressure, and if it happens, it is going to be irreversible process.
yes, sir. Got
Okay,
it.
right, cool, right. So
Sir,
everybody
why do
understood,
we,
right? Yeah.
sir, why do we consider that irreversible? Why is it like a straight line? And pressure
That's
is
what, no,
constant.
that's what I said. So this pressure, this is the external pressure here, right? Now this pressure is not going to change. This is constant external pressure, but the volume will change, right? The volume is going to increase. So obviously how the graph will look, this pressure should not change. Definitely it should be a straight line. Only then this value is not changing, but the volume has to increase. So the graph looks like this. Same goes here. Now if I look at here, after, okay, now I think, yeah, after adding the 110 kg mass, again the pressure is going to be constant. There is only 110 kg mass. The compression is going to happen under only one pressure, that is my pressure due to 10 kg mass. So again, this pressure is not going to change. So the graph will go continuously like this, but the volume will keep on changing. Yes.
Yes.
Understood why is a straight line parallel to
Yes.
x-axis, right?
Yes.
Okay, cool. We'll move on. Right. So now that we understood what you mean by reversible and irreversible, now we can go for different modifications of the first law, depending on what kind of process we are going to use, right? So let me take an isocoric. Oh, I think I don't like the color of the pen. I will go to red. Right. So if I take an isocoric process, right? So isocoric process is going to be a constant volume process. That means the volume of the gas is not changed. It's a sealed container. The volume, the gas cannot expand, the gas cannot undergo compression, nothing can happen, right? Okay, so now what is going to happen? So let me look at the first law, right? When I look at the mathematical form of first law, I have del E is equal to Q plus W. Okay, right? Now we know what is the formula for W. W is basically going to be minus P external del V, right? Now, okay, now what happens? Now, since it's an isocoric process, can I say the volume is not changing? So obviously del V is 0. So now what will happen to W? W also will become 0. So what do you get? You get delta E is equal to Q, right? So whatever heat lost or heat gain, whatever is happening, it is just changing the external pressure. Sorry, just changing the internal energy, right? Okay, now here I'm going to derive an important relationship for your Q. Important relationship for your delta E, right? So now since you're doing the process at constant volume conditions, right, let me call this Q as QV, means heat added or heat lost at constant volume. Okay, right? Heat added or heat lost at constant volume that's what is QV, which I've written there. Right. Now let me go back to the equation which I derived for Q in terms of CV and CP. So Q will be NCV del T plus NCP del T. Right. Okay. Now what we're doing here, we are doing the process under constant volume conditions. So this term has no role to play because that is at constant pressure. This is not constant pressure, right? So can I write the equation as QV, that is heat added or heat lost constant volume, to be equal to NCV del T? Right? So now this QV and this QV are absolutely same. Now I am going to get a beautiful relationship for delta. Now delta E is equal to N CV del T. That's it. This equation you are going to use for whatever the type of processes, because that is how I'm going to define my change in internal energy. How do I define it? Change in internal energy is the heat lost or heat gained at constant volume. As simple as that. Again, I repeat, heat lost or heat gained at constant volume is what is called as your change in internal energy. Okay, and if that's the case, this is the equation you will use. Now, from now on, not only for isochoric process, for any process, you can put the formula of delta E as NCV delta T. Again, you are going to remember this. A lot of times it will get used. Okay, so this is, now you have to remember this. Obviously, for an isochoric process, what is the modification? But the more interesting part of the story is this, right? You have to know the formula. We have derived a formula for delta E, exclusively for delta E, NCV delta T. Okay, right? Cool. Now we'll move on. We'll move on, say, to an isothermal process. Right? So an isothermal process, that means the temperature is constant, right? Isothermal means temperature is constant. So I can have delta E is equal to Q plus W. This is what is my first law, mathematical form of first law. And just now we found out delta E is NCV, NCV delta T, right? So now what happened? If it's an isothermal process, constant temperature, so delta T is 0. So definitely delta E is 0. So Q will be equal to minus W for an isothermal process, right? So this happens for an isothermal process. Q is equal to minus W. Okay, right? Fine. Now, actually, I'll be able to expand a little bit more on this isothermal process. Okay, right? So let me go for, and I see now it's pretty easy, right? There is no instrument to directly measure the amount of heat. No, not exactly. There is no direct way of measuring the heat, right? So if you want to measure what is the amount of heat lost or heat gained at some process, any process for that matter, you have to find something else, right? Say in this case, you have to find W. In this case, you have to find delta E. Then that can be equated to Q. Or if at all both of them are not zero, you find delta E, you find W separately, and then you put it in the first law equation to find the Q value, right? So there is no direct way of finding Q, right? So in this case also, you find the work done during this isothermal process, and the negative of that work done will be equal to your Q. Okay, now if it's an irreversible process, no issues, W can be easily found out, isn't it? W will be equal to minus P external del V. This is pretty easy, right? So minus P external del V, you just put the delta change in volume, put the external pressure, you'll be able to get the work done, and negative of that work done will be equal to your Q. That is okay. But if it's an reversible isothermal expansion, people, let me go for that. Right? So we are going for reversible isothermal expansion of an ideal gas, obviously, because you're going to use ideal gas equation here, right? Reversible isothermal or isothermal reversible expansion of an ideal gas. Okay, now how do we go about it? It's pretty simple. Now say I take a small dW, right? Now this small dW, I can write it as minus of, okay, I'm not putting integral now. So minus P external dV, correct? Right, minus P external dV, right? So now if I want to find the whole work done, right, I have to integrate. Obviously now the limits will be from initial volume V1 to the final volume V2, right? Now what I'm going to do is that I'm going to take this external pressure. I'm going to use my ideal gas equation, PV is equal to nRT. So I can write P as nRT by V, right? Now if I substitute that here, you'll be getting minus integral of nRT T by V dV, and still the limits remain same, right? So obviously temperature is constant, R is constant, N is constant, that can be taken out of the integration. So you just have dV by V, and hope you know the integral dx by x is log x, correct? And if you put all that, if you put the substitute the limits, upper limit minus lower limit and all that you put, I will be getting this W, and this W is for isothermal reversible expansion only. Please do not use the formula which I'm going to write for any process. It is exclusively for this. That is your reversible isothermal expansion of an ideal gas only. Please be very, very careful. Okay, so this W, if you substitute all the limits and put the integral, you will get 2.303 N R T log of V2 by V1. This equation you will remember, right? It's 2.303 nRT log of V2 by V1, right? So basically you will be getting log to the base E if you do this integral. So if you want to, if you want to put it in the natural log of the log to the base 10, right? You will multiply by 2.303. That's how this 2.303 came into the picture, right? So yeah, so that's how you do this. This is the formula for isothermal reversible expansion of an ideal gas. Now there's a negative sign, I suppose, yeah, there's a negative sign here, right? Now this equation can be a little bit modified using Boyle's law, right? So we know according to Boyle's law, we can have P1 V1 equal to P2 V2, right? So now that can also be substituted because I have V2 by V1 here. V2 by V1, I'll be able to write it as P1 by P2, right? So if I can even write one more equation in terms of pressure of the gas, this is not external pressure. This P1 and P2 is not the external pressure. These are the pressures of the gas. Okay, so this W will be equal to minus 2.303 N R T log of P1 by P2. Again, this formula also you can remember. Depending on what data is given to you, accordingly you'll use. Okay, so this is especially for reversible isothermal expansion. The formula you have to remember. Okay, now if it's an irreversible process, pretty simple. You don't have to use this formula. You just have to go for minus P external del V, and pretty simple, right? Okay, now there is one small thing I want to tell you guys. So when I go for this first law, right, now you know that this particular thing will be in joules. This will also be in joules, and this, if you use PV, that is P external del V, or just PV, what will you get? If you use say atmosphere ATM for the unit of pressure, and if you use liter for your volume, you will be getting the unit as liter atmosphere, right? So look at this, you have joules, and you have liter atmosphere. Please, at least now you know that you will not be able to add all these three. Only when the units are same, you will be able to add it. So before you conclude the problem, before you substitute the value here and you add it whenever a question is given to you, please understand this W value should be multiplied by 101.3 so that you will get the answer in joules. So very careful. Like even if you do all the things correctly, at the end, if you do not do this, the entire problem is wrong. Like you will not even find the options in the given multiple MCQ, right? So this you have to be very careful. This W, if you liter atmosphere 2 joules, if you want to convert, you have to multiply this W value by 101.3. Now here in this case, you don't have to worry about it, right? Because you will use the R value accordingly. R value will be in terms of joules, that is 8.314 in this case, right? Or if you want the answer, this is for joules. And if they ask you in terms of calories, it is going to be 2 calories. So just you put the R value as 2 there. And if it's going to be asked in terms of joules, you put the value as 8.314. right? Okay, so this small thing you have to be very careful, right? Okay, so this is about isothermal reversible expansion, right? Now let me go for your adiabatic. Right, if I go for an adiabatic process, we know what happens there. There is no heat loss or there is no heat gain. What is the time? Okay, we have half an hour, right? So we have, what is that? We have no heat loss, no heat gain. So if I write my first law, delta E is equal to Q plus W, right? Now what happened now? Since it's an adiabatic process, Q is 0, right? So what you just have is delta E is equal to W, right? So again, if you want to have an irreversible process, right? So I can directly put the W value as minus P external del V. Very simple. But again, you have to multiply it by 101.3, right? That and all is there. But if I go for same way, adiabatic reversible expansion of an ideal gas, so again, I'm going for adiabatic reversible expansion, right? If I go for reversible expansion of an ideal gas, right? So there is a big derivation, people, but you don't have to know. You don't have to know the derivation. You just have to know the formulas. I don't want to waste time in deriving it, right? So I'll directly give you the formula. It is not going to be a formula for W, right? But it is going to be an equation relating pressures on volume and temperature, right? So let me tell you how to go about it, right? So let me give you the equations first. So you have the first equation for the adiabatic reversible expansion to be PV power gamma is a constant value, or I can tell it as P1 V1 power gamma is equal to P2 V2 power gamma, or that is equal to P3 V3 power gamma. How you have Boyle's law, P1 V1 equal to P2 V2. Just like that, I just have one extra gamma for the volume. Only for volume this power, not for the entire term. Okay, this is only for the volume, right? Okay, so what is this gamma? Now let me tell you what is gamma is. That actually is a constant which comes from the derivation, right? So this gamma is nothing but R by CV minus 1, right? Gamma is equal to R by CV minus 1, or gamma is also equal to, what is the ratio of CP and CV. Okay, now obviously you know CP, I can write it as CV minus R, right? Or say R minus CV, something like that. And if you put it here, you'll be getting this equation, right? Okay, right? So R by CV minus 1 or CP by CV is the this gamma. Gamma is nothing but it is a coefficient of thermal expansion. Okay, gamma is called coefficient of thermal expansion. Okay, so this is the first thing you will understand, right? PV power gamma is constant, right? This is the first equation. Now, how will you go about problems? So in the problem, what will they give you is, say they might give you P1, they might give you V1, they might give you P2, but they will not give you V2. Now, what you have to do? You have to find V2, right? Or generally it will be in terms of, okay, let me see one. Let me come back to this. Let me write the second equation. Right. The second equation is going to be T V power gamma minus 1 is constant. Or I can write T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1, or is equal to T3 V3 power gamma minus 1. Right? Okay. Now let me explain with this. How will you go about the problem? Right? Say T1 is given, V1 is given, T2 is given, or say T2 is not given, V2 is given. Right? And they ask you to find the work done in this process. Right? Now what you have to do? You like, obviously now if you look at the equation, delta E is equal to W. So either if I find delta E, that will be equal to W, or if I find W, it will be equal to my delta E, right? So from this, we know the formula for delta E, that is NCV del T. So if I just know the final and initial temperatures, And if you know the CV value of the gas, right, the problem is done. If you find the delta E, and that is what is equal to W. So from this equation, T1 is given, V1 is given, T2 is not given, and V2 is given. Now, if you substitute all the values and find your T2 and put it in this equation, and you can directly get the W value. Delta E is equal to W. Okay, right? So this is pressure and volume. This is temperature and volume. And third also I'll give you, but very rarely you will use, and that is my pressure and temperature. So it will be P power gamma, T power 1 minus gamma is constant, right? P power gamma, T power 1 minus gamma is constant. But again, you will very, very rarely use this. Okay, but these two, that is this one and this one, yes, you will be using a lot of time. Again, I'm telling in terms of questions, whether frequency of questions. Okay, so we saw two things. Isothermal reversible expansion, you have a direct formula for W. In adiabatic reversible expansion, you don't have a direct formula, but you have an equation for connecting pressure, volume, and temperature. So you have to find T1 and T2, find your delta E, then find your W. That's how it goes in adiabatic. Okay, any questions, people? Any questions till now? Everybody understood?
Sir, I have a doubt. Sir.
Yeah.
Sir, shouldn't gamma be R by CV plus 1?
Once again.
CV plus R. No,
correct. Yeah, yeah. I'm really sorry. Yes, thank you. It's actually R by CV plus 1. Thank you. Yeah, it's R by CV plus 1. So if I substitute it, it will be CV plus R. Yeah, absolutely true. Correct. Yes. Right. So it will be R by CV plus 1 gamma. Any other questions? Right, I suppose everybody is understanding everything, right? So what else is there? I think we have to just have to go for some problems, but before that, there is one small thing which I have to tell you. Right now, answer me this question. Right, say now I have a chamber, right? I have a chamber and there is a piston arrangement and there's a gas, right? And say there is some block of mass and this is an equilibrium, some amount of mass. Okay, now and inside this chamber I have vacuum, right? Inside this chamber I have vacuum present, right? Now what I do is I remove the 10 kg mass, right? I remove the 10 kg mass, right? Now tell me, what is the work done here? What is the value of the work done here? Why is P external constant? Okay, I think you asked this question. Yeah, I answered it. Yeah. So what do you think is the answer? I mean, what do you think is the value of W here? Any random guesses?
A random guess.
Just
Zero,
use the
sir.
0, sir.
Okay, yeah, it is correct. How is it 0?
Something to do with the pressure, sir.
Yes, something to do with the pressure. What happened in a vacuum? What is the external pressure? What is the pressure?
Oh, 0, sir.
Absolutely right. So when a vacuum has nothing, so this has P to be 0. That is P external. Right, P external is actually 0 here. So what will happen? W is also 0. Px, because vacuum has nothing, no atmosphere, no nothing. So the only pressure is acting here is 10 kg. That's some mass. And if you removed it, the gas is undergoing expansion, but without any external pressure. Okay, so what you see here is that the gas is expanding, but still there is no work done by the gas because the external pressure is 0. So this particular case is what is called as free expansion of a gas. Right, so basically what is free expansion? Free expansion is an expansion of a gas under vacuum is what is called as free expansion. Okay, and then in that obviously the work done is 0. Right. Okay, give me a moment, guys. I'll just bring the problems. We'll do some problems. 1 second. Okay, guys, take this question. See, don't expect me to test you with your remembrance of problem, formula remembrance and all that. You already know the formula. It's all about how you can, what is that, get the trick of solving the question. So my questions will always be good questions, good quality questions, right? If you're not able to solve it, it's completely all right. Anyways, I'm there to help you, but I have to expose you to the level of problems. That is my job, and I'll do it. Okay, take on the question, people. 8 grams of O2 gas. 8 grams of O2 gas at STP. You have a lot of things to remember from 11th class. Okay, so 8 grams of O2 gas at STP is expanded to double its initial volume. 8 grams of O2 gas at STP is expanded to double its volume. Find the work done. Find the work done. Right? Yes, I'll give you 2 minutes. Quickly go through it and tell me if you can find the answer. It's pretty easy. I want the answer in liter atmosphere only. So I don't have to convert it to joules. Just tell me the answer in liter atmosphere only. So this is the formula which you have to use. W is minus P external del V. Now this is done, right? Del V I know is 2, double its volume, right? Initial volume and final volume is getting doubled. So del V value is 2, but external pressure is not given, right?
Sir, how is del V 2? It's 2 minus 1.
Ah, sorry, it's 1. Yeah. Sorry, this is not 2. This is 1. Yeah. So now how will you go for this? Okay, let me make a page. Let me help you with this. Right. Okay, so they have given me 8 grams.
Mr. Samshis, I request you to kindly mute yourself.
1 second, guys. Right, yeah. So I have 8 grams of O2 at STP. So this is enough conditions for me, right? Okay. Now what I have to understand is, actually, can I substitute? See, this previous page, what we did, that is, yeah. So previous page, we said that this del V is 1. No, we cannot tell that, right? How can we tell that? Say it will be, I can even tell it, I can say this del V, it will be V2 minus V1, right? So what they're telling is V2 is 2V1, right? So V2 is 2V1, this is V1. So basically it's not 1, it's basically going to be V1. Whatever the initial volume is, that is what is del V. Okay, so we have to find somehow the initial volume. Okay, so this is the small mistake which I mentioned. So we'll go back. Where are you? Oh, okay, it's here. Right. So I have 8 grams of oleic acid STP. Right. Now tell me, people, what is this STP condition? What do you mean by STP?
Standard temperature pressure.
Good, right? It's standard temperature and pressure. What is the value of standard temperature?
298 Kelvin.
No, that is NTP. NTP is normal temperature and pressure. That is room temperature and atmospheric pressure. STP, standard temperature, is 0 degrees Celsius.
273.
Yeah, 273 Kelvin. Right, it is 273 Kelvin. Okay, what is standard pressure?
1 atm.
1 atm.
Yes, absolutely. Right, it's going to be 1 atm. Okay, right. Now, let me go back to your 11th class first chapter. Okay, now tell me, what is the definition of moles with respect to volume? We know, we say 1 mole of something, we have some definition, right? There are three definitions for number of moles, one in terms of mass, one in terms of number of particles, the other in terms of volume. Okay, can you just list out all the three? Anybody can do that, or any one of you can do one, the other person can do the other one. What do you, okay, first let me ask the question. How do you define 1 mole with respect to mass? Okay, answer my question. 1 mole of sodium, what is the weight? Okay, maybe you don't. Okay, fine. You know, 23 grams. Okay, sorry. 1 mole of H2O, what is the weight?
18.
18.
Right. So now, how do you define it? Can you tell me? Yeah, what are you doing? Basically, you are 1 mole. If I say you are equating it to the molecular mass or atomic mass, isn't it? So that is how we define it. 1 mole of any compound or any atom will weigh exactly its atomic mass or molecular mass. Again, obviously 1 mole of anything at STP, we have to specify it. But anyway, still we don't have to. So 1 mole of anything will weigh exactly its atomic mass or molecular mass. That's the first definition. Okay. Now next, in terms of number of particles, how do you define it?
Avogadro number.
Absolutely, right? So now how will you define it? 1 mole of any substance at STP will have Avogadro number of particles. So for example, if I say 1 mole of sodium, means it will have 6.023 into 10 to the power 23 atoms of sodium in 1 mole. Same way, if I say 1 mole of oxygen gas, that means it will have Avogadro number of oxygen molecules. It's not atoms, because it's a molecule which you're talking about. O2 is a molecule. Sodium is an atom, right? Okay, so that is with respect to your Avogadro number in terms of number of particles. Okay, in terms of volume, how will you define it? Maybe there's something in the chat. Is there any? Oh yeah, there is something in the chat. Volume is equal to mass into density for O2. Density is not given, Kanna. Okay, what is the answer? In terms of volume, how do you define 1 mole? Nobody remembers. So this is how you studied 11th class, or was
So
it because
22.4 liters in it.
thank you so much. Right, that's the answer. Right. So 1 mole of any gas at STP will occupy a volume of 22.4 liters. So again, this is also at STP. This is also a gas, but it is not 1 mole. So if I have 1 mole of O2 at STP, this will have a volume of 22.4 liters. Hope you remember, guys. Some I think some lights are getting turned on, right? So I hope you remember, right? So 1 mole of any gas at STP, not only O2, any gas for that matter at STP will occupy a volume of 22.4 liters if I have 1 mole, right? So now there is a formula which connects your volume with number of moles, or you can even do by logic. Say number of moles N is equal to given volume divided by 22.4. So for example, if I find that a gas occupies 44.8 liters, that means how many moles? 2 moles will be there, right? Or say if a gas occupies only 11.2 liters, then I can say that only 0.5 moles of the gas is there, right? Okay, fine. So anyways, we need to find the initial volume for this particular gas at this condition, 8 grams of O2 at STP. If I can find my initial volume, the problem is done, right? So yeah, given volume by 22.4 liters is what is the formula, right? So now I have to find the given volume, but somehow I have to find the number of moles first, right? So for that, you have this. The given mass of this thing is given. So I have one more formula for number of moles. Given mass divided by molar mass. Hope you remember all the formulas, guys. These are simple formulas. I'm not going to touch the first chapter. Don't worry. Stoichiometry on I am really not going to touch. Right? Okay. So anyways, given mass by molecular mass is what is the formula? Now what is the given mass? Given mass is 8. What is the molecular mass of O2?
18.
What?
18th.
18.
16th.
32.
16 is the atomic mass of oxygen. What is molecular mass of O2? There are 2
32.
oxygen atoms, so it is 32. Yes, absolutely. Right? So it is basically going to be 1 by 4, 0.25 moles. Right? Okay. Now you got the number of moles, that is 0.25. Right? So now you know the formula, given volume by 22.4 liters. So now this into 0.24, 0.25 will give me the initial volume, right? So VI, I call it initial volume, will be by 4 of this, how much it will be? 11.2 by 2 will be 5.6, right? 5.6 liters is what is the what is that? Initial volume. Okay, now that's it. The problem is set, right, guys? So what happens now when I go for my W, it is just minus P external del V, right? Now what is the external pressure here? What is the external pressure? Given, right?
1 atm.
Exactly. STP is given, so it is 1 atm into V2 minus V1. And I know we said that volume is getting doubled, right? So it is just going to be V1 or VI, I call it. So it will be 2 VI minus VI, which will become VI. I think I explained the step before itself. That's it. So what is the initial volume? 5.6. So what is the answer now? Minus 5.6 liters is what is the answer. Don't forget the minus sign. If you do, I have an option of getting plus 5.6 and minus 5.6 in the choice in the question which I have itself. So if you miss the negative sign, again minus 1. Okay, in your JEE exams. Cool. So you have minus 5.6 liter atmosphere. I'm really sorry, guys. It's liter atmosphere. Right? Is the answer. Right? All already understood. We'll go for the next question. Okay. Right on this question, people. Okay, if I'll just give you time maybe for you to take this down. I'll give you 30 seconds. Okay, the next question, people. 5 moles of an ideal gas, 5 moles of an ideal gas at 27 degrees Celsius. 5 moles of an ideal gas at 27 degrees Celsius is allowed to expand isothermally from an initial pressure, you can just from Pi to be equal to 10 atm to Pf equal to 4 atm to a final pressure of 4 atm, right? Is allowed to expand isothermally from an initial pressure of 10 atm to a final pressure of 4 atm against a constant external pressure of 1 atm, against a constant external pressure of 1 atm. Find the work done.
Sir, can you repeat the question?
Yeah, I'll repeat the question. 5 moles of an ideal gas at 27 degrees Celsius is allowed to expand isothermally from an initial pressure of 10 atm to a final pressure of 4 atm against a constant external pressure of 1 atm. The question is, find the work done. Right? So comparatively, this question is little simpler compared to, I would say it's equally same, right? Okay, now tell me guys, there is one important thing which I told you and you are seeing it here. What is this? What you are seeing? Anybody can point out that special thing from the question statement?
Isothermal.
Expand as isothermally.
Okay, one is isothermal. Okay, next one. Some chat. What is this?
Ideal gas.
Ideal gas? No, yeah, it's an ideal. Like, even if they don't specify anything, we will assume only ideal gas. Okay, because real gas calculations are very, very difficult. So we'll assume whatever the gas given to be an ideal gas. That's not the thing.
The constant external pressure.
What is that? What does it tell you?
Isobaric.
No.
Sorry.
Against the constant external pressure, this phrase tells you what?
Irreversible process.
Absolutely, right? So this is how you find out, right? I told you this will be specified in the question. If they want you to know that particular process is an irreversible process, they'll specify the statement, right? That would be against a constant external pressure, right? So if you do not see the statement, people, if you really don't see the statement, then you have a natural tendency to go for the formula W is equal to minus 2.303 nRT log of V2 by V1. That is for an irreversible process. All the values are given. See, temperature is given. R value, you know, number of moles is given. So that formula exactly fits this description, right? But you should go for irreversible case because it's given under constant external pressure. So you just have to use minus P external del V only, not the other formula. Other formula is only for reversible. Be very, very careful on using the formulas, right? Okay. Right. Now you can do the question easily. It's just W. Is minus P external del V, right? Now external pressure is directly given to you, that is 1 atm. But the initial and final volumes are not given, but what is given to us is initial and final pressures, Okay. So basically it is 1 ATM into V2 minus V1 or VF minus VI, right? Now, how will you go about this? Tell me,
Sir,
how
you
can I
can
find
use
this
that
V2 minus?
VF by VI equal to PI by PF.
Okay, but we don't have VF by VI, we have VF minus VI. If I have VF by VI, yes, I can use directly P1 and P2, I can directly substitute here, right? But now what I have is V2 minus V1. So how will you go about this?
So we can use the number of moles equal to given volume by 22.4.
Given volume by 22.4, but this is not an STP. This is at 27 degrees Celsius, right? So if they're given STP, yes, what you said will work, right? But this is not at STP. This is at 27 degrees Celsius. So we cannot use that also. So what else can I
Sir, you can use
use?
a PV equal to NRT.
Absolutely, right? So we can use PV is equal to nRT, right? So I can write V2 as nRT divided by P2. Same way for V1, I can write nRT by, oh, yeah, nRT by P1, right? And that's it. Now temperature is constant because it's an isothermal process. Number of moles is given to you, 5 moles, and R value you have to know. And I want the answer in terms of joules. So what value you'll use? 8.314, right? And that's it. You have substitute here. So it will be 1 into, now see, nRT is here, nRT is here. It will be nRT by P2 minus nRT by V1. So I can even take nRT outside into 1 by P2 minus 1 by P1 is what is the answer. So I can just substitute the values and tell me the answer. Quick, 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 quick. Right, so you just have to substitute the values. 1 into 5 into 8.314 into temperature. Please remember, temperature should always be in Kelvin. If you substitute 27 as the thing, again done, -1. Please remember that. So here it is 300 Kelvin, 27 degrees Celsius. The Kelvin is 300 Kelvin. My 1 by P2 is 1 by 4 minus.
Sir, R should be 0.08 because in atmosphere it's going to pressure.
Yeah, but exactly. But that for that reason, correct. Atmosphere we're using. But if you want the answer in terms of joules, this will be taken care. If you put 8.314, it will be taken care. So not an issue. Okay, right? But
Okay.
if you use 0.0821, you have to, yeah, whole answer what you get should be multiplied by 101.3. So approximately this and this will have the same answer. I don't have to worry about it. Okay.
Sir, is it given in the question that you have to find in joules?
Yeah, it's the, I mean, it's not given in the question, but you can look at the choice. I didn't give you the choices. In choices, all the answers
Okay.
are in terms of joules. So that's how I find out.
Oh, okay.
Right. Yeah. Right. So I think will not waste the time in calculating QL. I just want to do one more problem. Right. Okay. So I can do the calculations later. Approximately, I can tell you 1 into 5 into 8. So I can just put the 8.314 as 8 itself. 5 into 8 will become 40. 40 into 300 will become 1200. 1200. This is 0.25 minus 0.1 will become 0.1. So zero point 0.1. Oh, wait. 5 into 4. Sorry, 5 into 8 is 40. 40 into 1000 to 1000. 200. Am I right? No. 12,000. So 12,000 into 0.1 will be around 1,200 will be the answer. Approximately, I'm very approximately telling guys, right? So it will be around, what is that? 1,200, something like that. Okay, if we just calculate. Okay, cool. No issues. Now we'll go for the next question. Take down the question, people. Guys, everybody understood, right? The previous question? Any issues? I just used ideal gas equation. Instead of V2 and V1, I just used nRT by V1, P1 minus nRT, okay, nRT by P2 minus nRT by P1. That's it. That's the only thing I did. Nothing else. And there's some question, maybe. Got it. Okay, cool. Right. So next question and last question for today. Please mind me. I'll just take 3 more minutes. It's a small question. Please take down. Right. Temperature of 1 mole of helium gas. Temperature of 1 mole of helium gas is increased by 2 degrees Celsius. Temperature of 1 mole of helium gas is increased by 2 degrees Celsius. Right? Now the question is, find delta E. Find the change in internal energy. Okay, I repeat the question. Temperature of 1 mole of helium gas is increased by 2 degrees Celsius. So they're asking you, find the change in internal energy, and I want the answer in terms of calories. Okay, I want the answer in terms of calories. Okay, now tell me, what should I use here? Which formula? Quick. Which formula?
So
I have to find
delta
delta
equal to
E.
Q plus W.
Okay, but I cannot use any of that, right? Q is not known, W is not known. So what formula?
Oh, NCV delta.
Exactly,
Sorry.
right? So you have delta E is equal to NCV delta T. Number of moles is okay. They are given 1 mole of helium gas. Temperature change in temperature is given, that is 2. I just have to know what is the CV value. Tell me, what is the CV value here? See, this is how questions will be asked. I told you the importance of remembering the CV values, right? Now tell me, what is the CV value here? It's a helium gas.
2R.
Helium is what kind? 2R. Okay, wait. Helium is what kind of gas? Monatomic, diatomic, polyatomic? What type?
Monatomic.
Obviously, all noble gases are monoatomic gases. Please remember, helium, xenon, neon, argon, all these are monoatomic gases. Okay, now helium being a monoatomic gas, right? So it will have only translatory motion, right? So what will be CV value?
3 by 2
1.5R.
1.5 R.
Exactly, right? It's 1.5 R, right? Because I told you the contribution of CV by translatory motion is 1.5 R, and I know monoatomic gases will have only one type of motion, that is translatory motion. So I can easily put the value here. Now it is 1 mole of 1 mole into CV is 1.5 into. Now I want the answer in terms of joules. 1.5 R should come. So what should be the value of R here?
8.31.
8.314.
I'm telling, I want the answer in terms of calories. Oh, did I say joules? I'm sorry, guys. Okay, I want the answer in terms of calories. What should be the answer?
2.
What should be the value of 2, right? So 2, because I want the answer in terms of calories. Into change in temperature is 2. That's it. So 1.5 into 2 will become 3. 3 into 2 will become 6 calories is the answer. Okay, right? So we'll do more problems. Don't worry, we'll do at least 3-4 problems next class, and then we'll go for the second part of the thermodynamics chapter. That is your thermochemistry. That is a little more interesting than this. If you find this already interesting, second and third part will be a little more interesting than this. Okay, so fine, people. Any questions? Anything you want to ask? 3 by 2 R. Yes, correct, Aditi. Yes, right. So yeah, any questions you want to ask? Any doubts? Okay, fine. Okay, guys, you can actually leave. We'll see next week on Saturday, right? Thank you so much. We'll meet again.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Thank you.
Thank you.
Yeah.